In the last lecture, we were talking about the different types of receivers, and we talked about absorbing versus non-absorbing. So we talked about that's not right. We talked about absorbing receivers last time. And we saw that the most important thing as far as absorbing receivers was concerned was the first arrival time. For non-absorbing receivers, now recall our diagram from a couple lectures ago. We have our transmitter over here releasing a molecule. This is the receiver over here. Actually, let's be more precise. I called this the region, script R. And my molecule propagates by Brownian motion. It follows a random path. And now if it's a non-absorbing receiver, the molecule, I assume, will cross the boundary and enter the region R. So what's most important for a non-absorbing receiver is to detect molecules within the boundary. So within this boundary, we have to be able to detect these molecules. And what's more, if there's many molecules that are transmitted, we potentially have to detect and count the number of molecules that arrive. So what's going to be important as far as non-absorbing receivers is concerned is counting and concentration. So to get a feeling for what's going on here with non-absorbing receivers, we're going to think a little bit about how this works in one dimension. So again, we're focusing on one dimension because that's the simplest possible case. So in one dimension, again, here's my line, the distance. Now I have my transmitter here at the origin. So that's x equals 0. That's where my Brownian motions start. And now I'm going to have a receiver. It's going to be an interval along this line. So I'm going to call these distances d and d prime. So this is my region R. This is my receiver. So what's going to happen is that one or more molecules is going to be released from here. They will do a random walk along this line, and they may or may not end up in here. What I'm going to do is I'm going to define an indicator variable. Alpha. And we are going to say alpha equals 1 if my Brownian motion is in the receiver, and alpha equals 0 if the Brownian motion is not in the receiver. So it's an indicator function. It's an indicator function indicating whether the Brownian motion is in the receiver or not. I'm also going to define, so the motion is random. The position at any time is given by b of t, Brownian motion. So at any given time, the position of this particle x is equal to the Brownian motion. The Brownian motion is random. There is some random chance that this particle will end up in here. So I'm going to say P alpha is equal to the probability that alpha equals 1, which is the probability that B of t is in the region. So in other words, P alpha is the probability over time that the molecule arrives in here. this will actually be a function of time because this distribution is a function of time, but we'll put that aside for now. So what is probability? What is P alpha? What is this probability? This turns out to be a key quantity. And if you think about, again, let me redraw that diagram. So to make this more concrete, we will assume particle is released at t equals 0, which means that my Brownian motion, the initial point of my Brownian motion, b of 0, b at time 0 is 0. So in other words, over here, b at 0 is equal to 0. So that's my initial point of the Brownian motion. So to be concrete again, what is probability? What is P alpha at time? Let's call it t. We know that from what we talked about earlier, the properties of the Brownian motion. B of t is distributed Gaussian with mean 0. I mean, the mean is simply given by the initial point. So if I started elsewhere other than 0, I would stick that here. And the variance of the Brownian motion, I'm gonna use the underlying variance of the Wiener process, sigma squared. That's sigma squared times t. So the probability, sorry, P alpha, which is the probability that alpha is 1, which is also the probability that B of t is in the region, is equal to the integral over the region of the probability density function of B of t. Actually, I'm going to give that the variable name x. And since that is simply given by the Gaussian, it's easy to write down. So P alpha, I am actually going to index this by t because it does vary with t. So I'm going to call it P alpha, comma t is equal to, like we said, it's the probability that the Brownian motion is in the receiver. And that is equal to, like I said, just redrawing this, the integral over the region of the PDF. Now, what is that? Coming back down here. The region R is the region from D to D prime. And it's a one-dimensional space, so this is a one-dimensional integral as x goes from D to D prime. My probability density function over here is the Gaussian probability density function with variance sigma squared t and mean 0. Oops, that's not right. It is x, e to the minus x squared over 2 sigma squared t dx. And in fact, this can be solved with, it can't be solved in closed form, as you know, unless you define your own special closed form functions, which we do have. They're called the error function. There's actually a variety of different ways to do this, but I like the error function. And what this will end up being is 1/2 error function d prime over root 2 sigma squared t minus 1/2 error function d over root 2 sigma squared t. And that's it. So if you know the error function, you can actually get p alpha t at each t, and notice that this probability is a function of t. So t appears here and here. I am going to include in the supplemental files along with this lecture, I'm going to include a Jupyter notebook that lets you play around with this function. So you can see a little bit about how that probability evolves. It's also going to be related, as we're about to talk about, to the impulse function, the impulse response for a molecular concentration pulse that is projected towards a receiver. Now, if you had drift, how would you change this? Well, how drift would change things would be, it would modify this term, wouldn't it? This would now become a function of, if we back up a bit, we would have a term VT here, which would mean we'd have a term VT here, and that would also appear in the error function. I'll leave that for you to do as an exercise. So let me just write that here, exercise. How does this change with drift? All right, so that's very nice. We now know how a single molecule will respond, but let's suppose instead, so the scenario I had at the beginning was I had my receiver region R, and maybe I had lots of molecules. Well, each of them has a Brownian motion. Some will end up in R, each with probability P alpha t at time t, and others will follow different trajectories. So for many molecules, some enter the region R, others do not. But the key observation is each molecule enters the probability P alpha t. So, maybe it's better to say, instead of enters, it's better to say is in R. So in other words, if I take, what I'm doing here is I'm taking snapshots at a particular time t, and I'm asking, are they in R or not? And that probability is given by P alpha t. So if I have n molecules initially, then what I have is the probability distribution. And what I'm interested in is how many are in R. So now what I'm looking for is the number that are within R. So if I pose that as follows, what's the probability that K out of N are in R? That is given by the binomial distribution. So I have N trials, that is to say N initial molecules. And my question is, I define success as arriving in R. So if I have K successes out of N trials, then that is the binomial distribution. With N and P alpha t. as the parameters. In other words, this probability, let's call it probability of k, is n choose k p alpha t to the k 1 minus p alpha t to the n minus k. And recall that we know exactly what this is. It's given over here. So you could, if you want, substitute that in over here, but just know that we can actually get that if we want. Now this is exact. The binomial distribution here is exact, but it's not very easy to deal with. So what we normally do is we realize that for large N and large K, this will approach the Gaussian distribution. So that's a well-known fact about the binomial, is that it'll approach the Gaussian distribution as the arguments get large. And it's actually not surprising at all. If you look back here, what do we have? We are basically looking at the sum. We're looking at the sum of a bunch of independent random variables. Remember my alphas, they're independent random variables. I have alpha equals 1 if it's in the region, and alpha equals 0 if it's out of the region. So therefore, what I'm actually calculating here is the sum of each alpha for all of these random variables, which means that I'm basically calculating the sum of a bunch of random variables from the central limit theorem. That implies that the distribution of that sum of alphas will approach the Gaussian distribution. Okay, what does that mean? What that means is that the Gaussian distribution is parameterized by mean and variance. So what I'm interested in here is the mean and variance. So mean and variance are needed. So the mean and variance of the binomial distribution. So, oops. If we go back here, just look here. So I have probability of K. So what I'm interested in is the average, the mean number of K. So the expected value of K. Now you can go look this up. It's easily found for the binomial distribution. But if you think about what's going on with the binomial distribution, you start with a bunch of binary variables and you add them up. So we have these alphas. We're interested in the sum of alphas. The distribution of that is exactly binomial. But if you have the sum of a bunch of Bernoulli random variables, each with mean, so the mean of those Bernoulli random variables is p alpha t. Then the sum of n of those, the mean of that will be n times p alpha t. By a similar argument, because they are all independent, actually this property, they don't need to be independent. If they are independent, then by a similar argument, the variance of k is equal to n p alpha t times 1 minus p alpha t. Now, for small n, I mean, this gives you a Gaussian random variable. But what I'm really interested in is what happens when n gets very large. So when n gets very large, the number k will tend to be close to the mean. To see that, the Gaussian, I'm just going to hand wave about this a little bit. The Gaussian random variable, or a Gaussian random variable, tends to be usually like 99% of the time within 2 or 3 standard deviations. This is the variance. This is the square of the standard deviation. So this is a hand waving argument. This is not a formal argument, but you can easily formalize this if you want to. And in the textbook that I wrote, Molecular Communication, I make a very formal argument about how this works. So you can read that if you want, but roughly speaking, here's what's happening. So we have the mean, expected value of k, is equal to n times p alpha t. The variance of k is n p alpha t times 1 minus p alpha t, which is greater than or equal, sorry, I'm going to upper bound that variance. So this is less than or equal to n p alpha t, just for simplicity, so I don't have to worry about this. So this is the largest value that I could possibly have for the variance. And that means the standard deviation is equal to the square root of the variance, which is less than or equal to the square root of n p alpha t. So my question is, how close are we to the mean? So if I have a mean of n p alpha t, and let's say I say 99% of the time I want to be within 99% of the time for a Gaussian, I am within 3 standard deviations. That'll be 3 root n p alpha t. So the p alpha t here is just a constant. It's not very important. But I can just pick some numbers here. So for example, in fact, just for simplicity, let's let p alpha t will normally be quite small. So let's just choose p alpha t is equal to 0.01. That means the square root of p alpha t is equal to 0.1. And let's let n be, let's say 1,000,000, 10 to the 6th. So that basically means I have, using this argument, you can probably see where this is going if you've ever thought about how large Gaussian values approach the mean. This means that I have 10 to the 4th on either side. That's 10 to the 6th times 0.01. And within 3 standard deviations of that, the square root of 10 to the 6th is 10 to the 3rd times the square root of p alpha t is 0.1. So that'll be plus or minus 300. So in other words, that's 10 to the 4th, which is 10,000. So the number inside the region will be between 9,700, which is minus 300, and 10,300, like 99% of the time. So that's actually a relatively small range, and you can see that if this number goes up, let's make it equal to let's let n be 10 to the 10th. Now this is still a very tiny number of molecules. 10 to the 10th is not very many molecules at all. think about Avogadro's number, a mole of molecules. That's like, that would be a reasonable number of molecules in normal circumstances, and this is like 16 orders of magnitude smaller than that. So this is still a tiny, tiny, tiny amount of molecules. In that case, I have, what is that? That is 10 billion. And my 99% interval here is, oh, excuse me, that's not right. It's 10 billion times 10 to the minus 2, which is 100 million. So I would have 100 million molecules inside my receiver with a 99% confidence interval of plus or minus, what's the square root of this? That's 10 to the 5th, that's 100,000 multiplied by 0.1. So that's 10,000 times 3 is 30,000. So on either side of that, I get 100 million. Sorry, that's 99 million. 970,000 and 100 million and 30,000. So the confidence interval becomes the size of the deviation with respect to the central number gets smaller and smaller, and that's because standard deviation scales as the square root of n, while the mean scales as n. So as n becomes larger and larger, the mean scales with n. While the standard deviation scales with the square root of n. So the number of molecules in the receiver approaches is close to the mean. Is very close to the mean. As a percentage of n. Again, you can make that argument a lot more formal if you want, but this is just sort of a hand wave. And what emerges from that is the concept of deterministic concentration. In other words, that's the idea that if you measure the concentration of a chemical in a beaker at the macro scale, you're not measuring a random number. You're measuring a huge number of molecules, and the deviation from the mean will be very small. But if you are at the nanoscale or the microscale and n is quite small, then this deviation is significant, and you actually do have to take into account the randomness. So what we just outlined there was counting, going from the nanoscale with small numbers of molecules to concentration, where we count large numbers of molecules. Everything is very, very close to the mean. I want to leave you with one thing here, and that is the time dynamics of concentration. And this is given by what's called Fick's law. You might also know it as the diffusion equation. So far in this lecture, we've talked about counting molecules within the receiver at a certain time, at a particular value of t. If you think about concentration, the way in which that becomes a time varying process is through Fick's law. I'm just going to very briefly and without a lot of technical depth explain where Fick's law comes from. So we have two, in fact, there are two Fick's laws. So the first Fick's law says the flow of solute, that's what you have dissolved across a boundary, is proportional to the rate at which concentration changes. That makes sense. So in other words, if you have a certain concentration here, a high concentration over here, and then a little distance later, you have a small concentration, then you will expect a flow to go that way. So how this is expressed as a differential equation is that this flow is equal to negative a constant of proportionality, D, times the change in the concentration. Now concentration here is expressed as a function of position and time. And here's the partial derivative with respect to space. So in other words, if there is a difference in space, this is in space. So this is in X. So this is at X, this is at X plus dx. If there is a difference in those concentrations, then there will be flow. This constant of proportionality, that's just the diffusion coefficient. All right, so this is so far only an expression of space. It's not an expression of time. So from that comes the second Fick's law, which works like this. Suppose, okay, so for uniform flow, i.e. f of x is equal to f of x plus dx. So the flow is uniform. There is no change in concentration. In time, because the same amount enters as leaves. The same solute enters as leaves. Okay, so imagine the picture here. Again, from x to x plus dx. If I have a flow here, and it's the same as the flow here, if that's the case, then the concentration will be the same because whatever leaves here enters here, and presumably there's also something else over here that's entering here. So basically the flow of solute will all be the same. On the other hand, suppose f of x is greater than f of x plus dx. Then some solute will accumulate. At f of x plus dx. In other words, if I have x here, x plus dx, and I have big flow here, and small flow here. Then lots of solute will be going from here to here, and little will be leaving. So there will be an accumulation over here. This can be represented in a differential equation as follows. So partial change of flow with respect to x is equal to negative the change in concentration with respect to time. So that's the second Fick's, that leads to Fick's second law. What you do is you take this guy, substitute it into the other equation. Now this lecture is running a little long, so I won't directly substitute that. I'll let you do it. But what you end up with by substituting into Fick's first law, you end up with this. Sorry, that's not dt squared, that is dx squared. And in fact, it generalizes to multiple dimensions. You just get the Laplacian here. This is called Fick's second law. It is often called just the diffusion equation. So with that, now we know how non-absorbing receivers work that count molecules within their boundary, and we know a little bit about their time dynamics.